Let's start off by eavesdropping in a storytelling session. Jagriti is telling her young son Abir a story. The Rabbit Problem by Emily Gravett. It's about a lonely rabbit who ceases to be lonely when he meets Chalk Rabbit. As the story unfolds, Abir sees how this rabbit family grows and how their growth mirrors a magical mathematical sequence. This episode of the Maths Factor is all about Fibonacci and his magical sequence. We will not only explore the sequence itself, but we'll see how this is mirrored in nature, in art, in the human body, as well as architecture. It's going to be a fascinating journey that will show you that mathematics is much more than formula and textbooks. So keep watching. Now back to Abir and the story of the lonely and Chalk. Now as the rabbit family expands in Fibonacci's field, here are some simple rules that we need to keep in mind. We start off with one male rabbit and one female rabbit, in this case lonely and Chalk. They will reach sexual maturity after 1 month. The gestation or pregnancy period of a rabbit is 1 month. And then the female rabbit will give birth every month to one male rabbit and one female rabbit. And rabbits never die, because this is math. So how will Lonely and Chalk's family grow through their first year together? Through January, it's just the two of them. In February, Chalk is pregnant, but we still have only one pair. By March, Chalk has a babies, one boy and one girl. So there is another pair of rabbits. For clarity, let's call this pair AB, making 2 pairs in all. In April, Chalk has another set of babies since she can have babies every month. Now, let's call them CD this time. And AB have reached sexual maturity and are expecting. So we have 3 pairs in all. By May, Chalk and Lonely have still another set of babies, EF this time. AB has a set of babies, GH, and CD have reached sexual maturity and are expecting. So how many pairs? Quite right, 5 in all. What happens in June? Lonely and Chalk produce IJ, AB produce KL, CD produce MN, and EF and GH are expecting. How many does that make? 8 in all. And it goes on like this. July will see 13 pairs, August 21, and on till the rabbits overpopulate poor old Fibonacci's field. Abir is quite delighted with these ever-expanding rabbit. Let's leave him for a bit and move on to the actual numbers of rabbits. Let's look at the sequence a little more in detail. If we list out the numbers, there is a pattern, isn't there? Each number is the sum of the earlier 2. 1 plus 1 is equal to 2, 2 plus 1 is equal to 3, 3 plus 2 is equal to 5, 5 plus 3 is equal to 8, and so on. This string of numbers is known as Fibonacci sequence after the man who wrote about it. Now Fibonacci's name was actually Leonardo of Pisa. He was Italian and lived in the 12th century. Through his youth, he traveled through Algeria, Egypt, Syria, Greece, Sicily, and Provence. Through this time, he had the opportunity to study under several mathematicians and was exposed to the Hindu-Arabic numeral system. He returned to Pisa in 1200, where he wrote his famous book Liber Abici, which means the Book of Calculations. Curiously, much of this book centered on introducing the Latin-speaking world to the Hindu-Arabic place-valued decimal system. In the last part of the book, which explored a series of interesting problems, Fibonacci studied the expanding rabbit brood that we looked at the beginning of the episode and worked out the famous sequence, which is what he is best known for today. It is interesting to note that Fibonacci lived in the days before printing, so his books were handwritten, and the only way to have a copy of one of his books was to have another handwritten copy made. Back to his sequence, let's look at it once again. Now, there seems to be enormous resonance with Fibonacci's numbers and patterns in nature. Let's start off by exploring how Fibonacci sequence in its basic form is found in nature. For that, we need to meet up with young Yukta, who is busy doodling flowers and trees in a workbook instead of studying for a math paper. Her enterprising mother decides to expose her to mathematics and nature instead of reading her a lecture. She pulls out a book and shows her a series of flowers. A pansy, which has 5 petals. A larkspur, which has 8 petals. A daisy with 13 petals. And an aster, which is 21. So what's common to all these flowers? Well, they're all numbers of the Fibonacci sequence. Now that Yukta is all fired up, her mother takes her to examine a tree next. If we look carefully at how a tree branches, we can see the sequence at work again. Let's see how that works. A main trunk will grow till it produces a branch. Then one of the new stems will branch in 2, while the other one lies dormant, leading to 3 branches. Then the first 2 branch into 2, while the third lies dormant, leading to 5 branches. The pattern is repeated for each of the new stems, and if we study the number of the branches as the tree grows, we get the Fibonacci sequence. We're exploring the fascinating ramifications of the Fibonacci sequence. In case you tuned in late, it's quite elementary. Each number here is just the sum of the last 2. Now we're going to take a look at a couple of related concepts which all stem from Fibonacci's sequence and have interesting ramifications. We are starting off with a team of children all holding squares. They are going to actually build a live model of what is known as the golden rectangle. Each is carrying a square that has a side that corresponds to a number in the Fibonacci sequence. Our youngest team member comes in to lay a 1x1 square on the lawn. The next square, which is also 1x1, is laid alongside. This forms a rectangle which is 2x1. Next up, we have a 2x2 square. We lay this on the longer side. This results in a 3x2 rectangle. We then add a 3x3 square on the longer side, resulting in a 5x3 rectangle. We then add a 5x5 square on the longer side, resulting in an 8x5 rectangle. And last up is an 8x8 square, creating a 13x8 rectangle. Now all these rectangles are known as golden rectangles. Their sides are consecutive numbers from the Fibonacci sequence. Now this golden rectangle is said to be one of the most visually satisfying of all geometric forms. We're going to see how this translates in both art and architecture. But first, I want to introduce you to the idea of Phi, or Mr. Phi, as we'd like to call him. He wonders how best to tell you the story of the ratio named after him. He pulls out his magic wand and first lines up the numbers of the Fibonacci sequence all over again. It then starts working out the ratio of consecutive numbers in the sequence. Doesn't look particularly magical, does it? But as he works his way down, the ratio will slowly approach a number that is close to 1.618033 and so on, which is called the golden ratio of phi. Now the thing to remember about phi is that it is really long. In fact, it is endlessly long. Numbers like this which don't end are called irrational numbers. Now if Mr. Phi is trying to be more high-tech and accurate, this is how he would have defined himself. But he doesn't want to confuse you, so he's happy to put it aside for the moment. Now Mr. Phi is not just a cool endless number, but recurs in all kinds of interesting places. First off, let's look at the dolphin. If we stop one of the dolphins for a minute and measure the distance from the head to the navel and the navel to the tail, we will get two consecutive Fibonacci numbers, which means the ratio of the two is Mr. Phi. Honeybees follow Fibonacci in even more interesting ways. In a colony of bees, there are always more females than males. The ratio of females to male is usually very close to phi. If you look at the bee family trees, another interesting pattern will surface. Males have one parent, a female, whereas females have two, a female and male. Thus, when it comes to the family tree, males have 2, 3, 5 and 8 grandparents, great-grandparents, great-great-grandparents and great-great-great-great-grandparents respectively. Following the same pattern, females have 2, 3, 5, 8 and so on. Now, there's a fair amount of Fibonacci in our body. A person who explored this is the famous Renaissance painter Leonardo da Vinci. You know about his art, but did you know that Leonardo was quite a mathematician also? Let's look at one of his famous pieces of work, The Vitruvian Man, which is Leonardo's study of the proportions of man. You must have seen it somewhere, but have you ever wondered what all those lines are about? Well, these lines connect with the golden rectangles. In fact, there are 3 distinct sets, one for the head area, one for the torso, and one for the legs. Let's start with the head. If we draw a rectangle whose base goes along the man's neck from shoulder to shoulder, the top of the rectangle should meet the top of the man's head. This creates the first golden rectangle. Inscribe a square in the left side of the rectangle, creating a smaller golden rectangle on the right side of the man's head. Then do the same with the right side of the original rectangle, creating a long thin rectangle that runs vertically through the center of the man's head. Did you note that the rectangles intersect with the focal points of the head, the eyes? Now for the second set of rectangles. There's a rectangle which runs from elbow to elbow and from neck to waist. This creates a golden rectangle. For the third set, draw a rectangle whose lower 2 vertices are at the places where the man's outermost toes touch the outlying circle. The rectangle should extend vertically to the man's waist. This creates yet another golden rectangle. The proportions of the Vitruvian Man are believed to be ideal proportions for the human figure. Let's move to the Mona Lisa, arguably the most famous painting in the world. Considered to be Leonardo's magnum opus, it depicts a woman whose gaze meets the viewers with an expression often described as enigmatic. Now this painting also seems to be inundated with golden rectangles. It looks like Leonardo has almost purposefully tried to incorporate mathematics into his art. We're exploring Fibonacci and his wondrous sequence. Our explorations take us to the city of Chandigarh, the capital of Punjab and Haryana, where we will explore the work of a famous architect who deeply believed in the golden ratio. We are talking about none other than the famous Swiss-French architect and painter Le Corbusier. Seema Bhalla, an art historian and Corbusier expert, wanders through the Le Corbusier Center. Born as Charles-Édouard Jeanneret Gris, Le Corbusier chiefly built with steel and reinforced concrete and worked with the elemental geometric forms. He was called into India to plan the city of Chandigarh, the new capital for the states of Punjab and Haryana. Corbusier was fascinated with the idea of the golden ratio. He developed Le Module, the figure of a man based on golden ratios. His inspiration was Da Vinci's Vitruvian Man. Corbusier believed that this ratio worked beautifully in architecture. Seema now heads out into the city to explore how he applied the modular to many of the government complexes he built in the city. Corbusier is believed to have planned the entire layout of the city based on the modular man. So the head contains the capital complex, the heart is the commercial center, and the arms have the academic and leisure facilities. Many of the key structures in the city also reflected this ratio. Like at the High Court, where the golden ratio is reflected in the marvelous main structure along the pillars and the windows. Similarly, the golden ratio can be in every window section of the Secretariat. Incorporated in this scenario is the famous hand of the modular man. Corbusier's rationale for bringing in this proportion in his architecture was his belief that human life was comforted by mathematics. Corbusier hoped that his system would one day be used to standardize all aspects of construction throughout Europe and possibly worldwide. He had patented the concept and was looking forward to huge financial reward. If we travel further afield and further back in time to, say, Greece, we can see this ratio in much of the classical architecture in this country. Take the famous Parthenon in Athens. If we work out the lines of the Parthenon, we come up with a whole series of golden rectangles. Many other classical monuments, like the Acropolis of the Chartres Cathedral, echo these proportions. Now, we are going to explore what is called the Fibonacci spiral. But how does this spiral connect with a mathematical sequence? Well, Akanksha has decided to try and figure out how a Fibonacci spiral forms from the Fibonacci rectangle. She picks up a compass and moves towards a panel containing the rectangles. First, she sets the compass to the length of the first and second square, places it at the center of both squares and draws a semicircle like this. She then adjusts the compass to its length in the side of the second square and draws up an arc like this. She then continues drawing arcs until all the squares each have the curving spiral through them. And voila, Akanksha has a Fibonacci spiral. Now this spiral is seen in nature in shells like this nautilus shell. It is even seen in the cochlea of a ear. Now Akanksha is curious to see if she can actually find the Fibonacci spiral in nature. She picks a pineapple to study and carefully studies it. When you look carefully, the rows spiral out in 3 directions. She then counts the rows in 2 of the directions. She marks each row with a pin. This can take a while because every pineapple is not perfect. But if you're careful, you can do it. She finds that the number of rows in one direction is 8. The number of rows in the second direction is 13. And these are consecutive Fibonacci numbers. Interesting, right? It's similar in a sunflower. The seeds form a spiraling pattern. If we count the number of spirals in each direction, they'll be neighboring Fibonacci numbers. We can see similar patterns in pine cones, cacti, and some aloe vera. It's been quite a whirl, our journey through the magic of Fibonacci. We have seen animals and plants, art and architecture, human bodies and honeybees. We could keep going on, exploring golden triangles, pentagrams. The list keeps going up. But we'll save that for another day, for another episode of the Maths Factor. Keep watching to catch more fantastic mathematical connections that make our world so magical.